the final chapter in this class. You have made it. Congratulations. And the final chapter here is actually my favorite chapter in this class, which is the nuclear chemistry chapter. It's a lot of fun, I think anyway, to talk about nuclear chemistry. Even though when most people think of nuclear anything, this is what they think of. They think of death and danger and cancer and the bomb. It's all bad things when most people think of nuclear topics. But in reality, nuclear chemistry is so much more than just the bomb. It is so much more than just death and destruction. So, for example, in the Voyager space probe, and for really any space probe that is way far away from the sun, they have to be powered by something, and it ain't solar panels. If you are a space probe and you just took pictures of Pluto, as I forget what the name of that probe was, but that probe is so far away from the sun that solar panels aren't going to do anything. Solar panels wouldn't be able to light up an LED board that far away from the sun. It needs something that has some oomph to it that can last a really long time, even when it's out in the cold of space. And nuclear batteries can do that. These are batteries that actually have nuclear material in them that are hot all the time, and that heat is actually used to generate electricity. The same thing is actually found in pacemakers, believe it or not. If you have a relative that has a pacemaker in their chest, most likely, as far as I'm aware, all the time, but there's exceptions to almost everything, but the vast majority of pacemakers are actually powered by nuclear batteries. There's actually a relatively small amount of nuclear material inside the pacemaker that powers a battery that runs the pacemaker. Similarly, there are a lot of medical situations where you use nuclear processes to produce radiation that you can use to scan people, which is what you see up here. Things like PET scans use nuclear decay to allow you to scan someone for certain things. And also, if we didn't have nuclear processes happening, we would all be dead and never would have even existed in the first place, because the sun, which is the foundation of the food tree, so to speak, because you have plants and things that get their food from the sun in the form of light and the nutrients as well, but they need light. And then other things eat the plants, and then we eat the things that eat the plants. So we get our food from the sun in a sense, but also we get most of our heat from the sun as well. We wouldn't have any kind of weather. The planet would be just a cold, dead rock without the sun, which is powered by nuclear fusion. So there's a lot more to nuclear science than just the bomb. There's a lot more to it than just radiation. So, before we get into more of the applications for nuclear chemistry, we're going to talk about what's actually happening in these nuclear reactions. Now, hopefully you remember from Gen Chem 1 how to write and interpret a chemical symbol. So, the symbol from the periodic table is usually in the middle there, and then we will sometimes have the atomic number written in the bottom left corner. The atomic number is the number of protons. Sometimes that's written, sometimes it's not. For our purposes, we are going to usually write it in this chapter because we actually do care how many protons something has. Most of the time in previous chapters, we didn't really care. We would just look at the periodic table if we wanted to figure out what its atomic number is. And then the mass number is given in the top left corner. Now the mass number, if you remember, that is the number of protons and neutrons added together. So this particular isotope of carbon, because it has 6 protons, also has 6 neutrons because its mass number is 12. Hopefully that makes sense. Hopefully you also remember from Gen Chem 1, just generally at least, what an isotope is, because we're going to be talking about isotopes a lot in this chapter. But just to refresh you, in case it's been a little while, An isotope of an element is just, well, let me rephrase that. Elements are made up of different isotopes. So every element has multiple isotopes, and what distinguishes one isotope from another isotope is the number of neutrons. So every isotope of an element will have the same number of protons, by definition. If you have a different number of protons, then you're not the same element. The number of protons defines the element. The number of neutrons, on the other hand, will just give you changing the number of neutrons will give you a different isotope. So, for example, uranium comes in 3 different naturally occurring isotopes: uranium-234, uranium-235, and uranium-238. So there is a difference of 4 neutrons between the 234 and the 238. The 238 is the most stable, by far, of those 3, and most of the uranium on the planet, like 99.99% of the uranium on the planet, is uranium-238. But uranium-235 is the most common of the unstable isotopes, as we'll talk about in a minute. The uranium-234 is also unstable, but it is much more rare than uranium-235. Other examples of isotopes here. Hydrogen actually has 3 naturally occurring isotopes as well. There's the normal, so to speak, hydrogen, which the sciencey name for that is protium, where it has just a single proton and a single electron. If we add a neutron to that, we get deuterium, which you might have heard of. And then there is tritium, if we have 2 neutrons with the proton in the nucleus. And that is indeed the tritium from the Sam Raimi Spider-Man 2, which is a decent movie, and the science involving tritium is not 100% terrible in that movie. That's not what tritium looks like, but tritium is actually very, very useful for creating artificial fusion. So they were not wrong about that. They were just kind of they were wrong about other things, but they were correct that tritium is very useful for creating artificial fusion. All right. So we have these different isotopes of elements. It's not uncommon for some nuclides or some isotopes. A nuclide, by the way, is just another name for the nucleus. It's specifically one specific isotope of a specific element is called a nuclide. So it's not uncommon for some nuclides of an element to be unstable or radioactive. So these nuclides, these specific isotopes that are radioactive, we call radionuclides or radioisotopes. So we have kind of like 3-4 different words for the same thing here, but hopefully you won't get too confused by that. But radionuclides or radioisotopes are specific isotopes that are unstable. They are not going to hold together given enough time. Just because something is unstable doesn't mean that it's going to break apart 2 seconds from now, but eventually it will. It just depends on how unstable it is. When these things do decay, when they do break apart eventually, there's multiple ways they can do that. It's not just a one-size-fits-all. There is more than one way they can break down, more than one way they can decay. Before we get into that, though, and actually we'll do that in the next video, I do want to briefly talk about Marie Curie. She was the first person to study radioactivity in detail. And at the time, when she was studying it, she didn't actually know that it was dangerous. She and her husband, and I believe a few other people as well, but mainly her and her husband, were the ones that were studying it. Someone else actually discovered it. I forget the guy's name, but there was a guy that discovered radioactivity by accident. And his response was essentially, interesting. Moving on. And never really looked into it from that point forward. He told some other people about it, which is how Marie Curie found out about it and started to investigate that. She was able to see the significance of that. But she and her husband spent most of their chemistry life, so to speak, working on radioactivity. They discovered 2 elements during their studies. So she named them after her home country of Poland. So polonium, if you've ever heard of that, she discovered that. She named it after Poland, which is where she grew up. She did most of her research in Paris, but because she grew up in Poland, that was her home country, and she named it the element after it. And she also discovered, I believe, radium. I get radium and radon mixed up a lot, but I believe she discovered radium, and she named it after radiation. So sadly, because she did not realize at first that these radioactive elements were dangerous, she would be working with it out on her desk, just a chunk of uranium sitting on her desk next to her as she would work on stuff. At one point, her husband licked a piece of uranium to see what it tasted like, because essentially, things were different back in the early 1900s, which is when most of this research was being done. I believe it was like after World War I, but before World War II was most of when this research was being done. And apparently they would lick stuff back then. It boggles the mind, but they did. He did. He licked the uranium. And so they both would end up dying from radiation poisoning. Not instantaneously or anything, but just from the chronic exposure to radiation, she would eventually die from that. Her daughters would carry on her research actually after her with better protection. So I do not believe either of them died from radiation poisoning. But anyway, she was a really amazing woman. And if you are interested in doing any kind of research into female scientists, she would be at the top of my list as a suggestion for you. But again, I am a bit biased because I like nuclear stuff in the first place. So. But she, just another quick thing about her, she was the first, and I believe, I might be wrong about this, but I know for sure she was the first person to do this, and I believe she's the only person to have won 2 Nobel Prizes in different disciplines. I believe she won a Nobel Prize for physics and a Nobel Prize for chemistry. And I know for sure she was the first person to do it. Not just the first woman, the first person to do that. And I think she's still the only person, but I could be wrong about that. So there's something for you to research. So in the next video, we will start talking about the different kinds of radioactive decay that can happen, and then we'll move on from there. So I'll see you all in the next video.